Assalamualaikum warahmatullahi wabarakatuh. My name is SYAHRIL NIZAM bin Abdul Halimi, nometrik 231543945. I will be presenting my project on battery thermal management system. Part 1 is a problem identification. The main issue we are facing is that the lifespan and life safety of lithium-ion battery rely heavily on their operating temperature. If the battery overheat, it will experience rapid capacity degradation and is prone to the risk of explosion due to thermal runaway. Conversely, if it is overcooled, the driving range will decrease and charging time will become very slow. The current industry challenge is that a cooling system are highly inefficient with liquid cooling at significant weight and high cost. Part 2. Technology review. Let us examine the 4 existing technology. First, air cooling. It is cheap and lightweight, but its heat dissipation capability is very poor. Second, liquid cooling. It is highly efficient, but at heavy weight and system complexity. Third, phase change material or PCM. This material is excellent at maintaining uniform temperature, but its weakness is that it is slow to release the heat it has absorbed. Fourth, immersion cooling. It offers outstanding thermal performance, but its engineering level is highly complex for mass implementation. Alright, part 3, case study. Moving on to real-world evidence, let us examine 2 constructing case studies that clearly highlight the critical importance of effective thermal management. First, we have the early generation of the Nissan Leaf. This vehicle utilized a strictly passive air cooling system relying entirely on ambient air to dissipate heat from the battery pack. Industry report and real-world consumer data have proven that this lack of active cooling caused the battery pack to suffer severe heat degradation, particularly when the vehicle were operated or parked in hot climate. The inability to actively shed heat lead to accelerated chemical breakdown within the cell. On the entirely opposite end of the spectrum, we have the Tesla Model 3 and Model Y. This vehicle employ a highly sophisticated active liquid cooling system, specifically a unique liquid ribbon tube design that snaps directly between the cylindrical battery cell. This specific geometry maximizes the contact surface area for heat transfer. By circulating a liquid coolant, the system successfully and consistently maintains an optimal operating temperature range between 20 and 40 degrees Celsius, regardless of external weather conditions. This active regulation prevents localized hotspots across the battery pack, thereby significantly prolonging the overall lifespan, reliability, and performance of the battery. Alright, part 4. Propose solution to bridge the gap between existing methods. I propose an advanced hybrid thermal management solution. This design strategically combines the immediate thermal absorption of phase change material or PCM with the continuous heat extraction of liquid cooling. It operates through a highly engineered 2-layer mechanism. The first layer as immediate thermal buffer with PCM directly wrapping around each individual battery cell. By utilizing latent heat, the PCM rapidly absorbs sudden extreme heat spike without significantly raising its own temperature. This is incredibly crucial during high stress scenario like ultra fast charging or sudden heavy acceleration. However, since a phase change material can eventually become fully saturated, we introduce the second layer and active liquid cooling network flow continuously just outside the PCM layer. This circuit steadily dissipates the thermal energy temporarily stored by the PCM, carrying the heat away from the module and rejecting it into the environment. And certainly, the PCM handles under thermal load while the liquid provide constant heat extraction, creating a perfectly balanced hybrid system. Part 5. Impact Analysis. The implementation of this hybrid system brings massive long-term impact across three crucial aspects. First, safety. By eliminating the risk of battery explosion through our dual-layer temperature control, we drastically reduce the fire hazard often associated with high-performance electric vehicles. This builds consumer trust and meets strict automotive safety standards. Second, economy and performance. Thermal degradation is the number one enemy of battery health. By consistently maintaining the optimal temperature range, we extend the battery overall lifespan. This directly lowers to the total cost of ownership for users by saving them thousands in expensive battery replacement costs. Finally, the environmental impact. A longer lasting battery means a significant reduction in the generation of hazardous electronic waste. This aligns perfectly with the global sustainability goal and the ongoing shift towards greener automotive solutions. Part C. Project Objective. To systematically realize this solution, this project is guided by three specific and measurable objectives. Our first objective is to deeply analyze and identify the root cause and pattern of heat generation in lithium-ion battery pack, specifically focusing on extreme operating scenario like rapid discharging. The second objective is to design a highly accurate three-dimensional computer-aided design model for proposed hybrid system. This involves detailing the structure layout of the phase change material and optimizing the fluid flow path to ensure minimal pressure drop. Our third and final objective is to rigorously evaluate and compare the thermal performance of this new design against standard industry system. We will rely on advanced computer simulation to validate whether our hybrid approach truly outperforms existing single method cooling strategy. Alright, the part 7, methodology or approach. To achieve this objective, our methodology is divided into 4 comprehensive phases. The first phase is data gathering. We will collect precise engineering specification for the 21,700 type battery cell, including their internal resistance and specific heat capacity. We will also determine the thermophysical properties of our choose phase change material and cooling fluid. The second phase involves advanced three-dimensional modeling, where we will design the battery pack layout and the intricate cooling channel using industry standard engineering software. The third phase is the core of our technical work, thermal simulation using computational fluid dynamics. We will set up boundary conditions to simulate real-world driving stress at various discharge rates, namely 1C, 2C, and 3C. The final phase is rigorous data analysis. Here, we will extract the simulation result to evaluate the maximum temperature, known as Tmax, and the temperature difference or delta T across the entire battery module to ensure it stays well within safe operational limits. Alright, part 8, project plan and timeline. To ensure all tasks are executed smoothly, this project is scheduled to run over a 14-week timeline. Week 1 and Week 4 will focus heavily on problem identification, literature review, and gathering all necessary technical parameters. Week 5 to Week 7 are strictly allocated for the three-dimensional modeling and design optimization phase. allowing ample time to refine the geometry. Next, week 8 to week 10 are dedicated to setting up running the computational fluid dynamics simulation. This include a closure buffer period to troubleshoot any technical issue that typically arise during complex fluid simulation. Finally, week 11 to week 40 will conclude the project with comprehensive data analysis, finalizing the technical report and preparing the present material. That conclude my presentation today. Thank you.